Good morning and welcome back. In this section, this last section of Chapter 7, we are going to be looking at a very specific type of problem that's called a rate-in, rate-out problem. Now, this type of problem has a lot of real-world applications because there's usually more than one factor acting upon any given situation. In these, we'll be dealing with typically two, one a rate going into something, one a rate going out of something. Now, what do these look like? These are you're filling a pool, but it also has a hole in it, so the water's going in, the water's going out. That's a kind of a standard type of problem. But it's also you're making hot dogs for an event and you're cooking them at a certain rate and you're selling them at a certain rate. So you have the rate in and the rate out. So it has a lot of applications for this type of problem. And so, what do these problems look like? These problems, you're always given a couple pieces of information. It's typically you're given a rate going in and a rate going out. Now, it's not always that way. You could be given an amount, but almost always I'd say you're given two different rates. Now, you're not always given the rates as equations. Sometimes they could be equations, sometimes they could be graphs, sometimes they could be tables. A lot of times you'll be given one rate as a table and one rate as a graph or as an equation because that will force you to find a Riemann sum and you'll have to do an antiderivative or an indefinite integral. And so that's what the way that it is a lot of times, but it could be two equations. You could have a graph. Um, it could be a lot of different things. Um, you may be given an initial condition, which would be a starting amount. You may be given um, other pieces of information that, these problems will vary from problem to problem. And then things that you'll be asked. You'll be asked to find a total rate at a given time. You will be asked to find the amount that changed going in, the amount that changed going out, the total amount that changed, the total amount of something at a certain time, which would use that initial amount. But you'll be asked a variety of things, not all in the same problem, but usually a couple different things per problem. And so we have a problem that we're going to look at that deals with a lot of these different things. And so this is a very typical type of problem. There's a lot of writing on this one. In this problem you have um, in your book as well. So it says the figure shows an above ground swimming pool in the shape of a cylinder with a radius of 12 feet and a height of 4 feet. The pool contains 1,000 cubic feet of water at time t equals 0. That right there is your initial condition. At time 0, it has 1,000 cubic feet of water. That's going to come into play in part D. So during the time interval from 0 to 12 hours, water is pumped into the pool at a rate of P of T, and that's shown in the table. We have P of T, so we're given a table for the rate in. And then during the same time interval, water is leaking from the pool at a rate R of T, cubic feet per hour, where R of T is that equation, 25e to the negative 0.05 t. And then it gives you the volume of a cylinder, because that's going to be important, again in part D. And then it says A, use a midpoint Riemann sum with 3 subintervals of equal length to approximate the total amount of water that was pumped into the pool during the time interval t equals 0 to 12 hours. Show the computations that lead to your answer. And so, for part A, we're going to use the table, and we need 3 time intervals. So we'll go from 0 to 4, from 4 to 8, and from 8 to 12. The midpoint Riemann sum means we're going to use the center y values. So the volume that goes in, volume in, will equal 46 times 4. Because the width is 4, the width for all of these is 4, plus 57 times 4, plus 62 times 4. Now, what we just wrote down would be showing the computations that lead to the answer. We don't have to show every single step. How do we go 46 times 4? How do we do 57 times 4? How do we do 62 times 4? We don't actually have to show that. We needed to show this step right here, which is setting up the problem. From here, we could go straight to our answer. Volume in is going to be, they're all times 4. We could factor out the 4, add together the 46 plus 62. That'll be 108 plus 57 is 165. Times 4 is going to be 660. So it's going to be about 660 cubic feet. In these problems, the units are important. Always have your units. So it's 660 cubic feet. And that's going to be about, because all we have is the table. So the midpoint Riemann sums are generally fairly accurate, but it is about 660 cubic feet. For part B, tells us to calculate the total amount of water that leaked out of the pool during the time interval 0 to 12. So the volume out is going to be the antiderivative from 0 to 12 of r of t dt. We have to use the leaking out one. So volume out will be the antiderivative from 0 to 12 of 25 e to the negative 0.05 t dt. It's important to have one of these written down. You don't actually have to have this second one written down. You could keep it with r of t. Here, we can find the antiderivative of this without too much trouble. Because the 25 e to the something will be 25 e to the something divided by the derivative of the something divided by the 0.05. 25 divided by 0.05 is just 500. So this will just be negative 500 e to the 0.05 t from 0 to 12. Now plugging in 0 is not too hard. E to the 0 is 1 times negative 500 is just negative 500. But plugging in 12, we're not going to do e to the 12 times negative 0.05 in our head or even by hand. That would be a calculator type of problem. Being that it's a calculator type of problem, we could actually just plug in the integral and have it do the integral for us. Either way, it doesn't matter so much. You could actually go from this first, the volume out is the integral from 0 to 12 of r of t dt, to the volume out equals, if we run that integral, we're going to get 225.59-ish, 225.59 cubic feet is how much water went out during those 12 hours. So we had water going in, we had water going out. And then part C, use the results from part A and B to approximate the volume of water in the pool at time t equals 12. Round your answers nearest cubic foot. So a lot of times what people will do is they'll just go, it's going to be 660 minus the 225.59, which is not wrong. We'd get 434.41, but we're going to round to the nearest foot. So 434, that's not a 4, 434 cubic feet, but that's not the water in the pool. That would be the change in the water in the pool. Over those 12 hours between what we put in and what leaked out, we added 434 cubic feet of water. It's asking for what's the total amount of water in the pool at that time. Remember that we started with 1,000 cubic feet. So we have to go 1,000 plus that, which will equal 1,034 cubic feet of water. And so that's how much will be in the pool at the end of the 12-hour interval. And so again, it's that initial condition that gets people. They'll do everything, but they'll forget that piece. It's an easy piece. It's an easy point to lose that you don't want to lose. Save the points that you lose for the hard questions. Don't lose the points on the easy questions. And so that's part A, B, and C. We need part D. We need a little more room for that one. So there we go. Part D. Find the rate at which the volume of the water in the pool is increasing at time t equals 8 hours. How fast is the water level in the pool rising at t equals 8 hours? Indicate the units of measure in both answers. So find the rate at which the volume of the water in the pool is increasing. The rate it's increasing, we can add and subtract rates. We have the amount of water going into the pool. The rate the water is going into the pool at 8 hours is going to be P of 8 minus the rate that it's leaking, R of 8. P of 8 is from the table. That's just going to be 60 minus R of 8 is going to be 25e to the negative 0.05 times 8, which again is going to be a calculator issue. You actually don't even need to write this part out. You could go P of 8 minus R of 8 equals about 43.24, and then include units. What's the unit? Well, the unit it's a rate. It's cubic feet per hour. All these rates are in cubic feet per hour. So that's that rate. And then how fast is the water level in the pool rising at t equals 8 hours? So how fast is it rising? How fast is that height changing? For that, that's going to be a related rates problem. We saw these a few chapters ago. So we're going to have the volume equals pi times r squared. R is just 12 feet, so we're using the volume of a cylinder. We're using that guy. R squared is just 12. That's a constant. We can plug in the 12 there. Times h, which means the volume equals 144 pi times h. We can find the derivative with respect to t. dv over dt equals 144 pi dh over dt. We're looking for the dh over dt. The dv over dt is what we just found. That's the rate at which the volume is changing. So we can plug that in. 43.24 equals 144 pi dh over dt. We just need to divide. So dh over dt will equal 43.24 divided by 144 pi, which comes out to be about 0.0956 feet per hour. It's not cubic feet anymore. This is the height. How fast is the height changing? The height is measured in feet. It's a linear dimension. And so we have the units there. We have the units up top. Again, it's important to include the units, especially when it tells you to. That is a surefire clue that this including the units is worth points. And it's again another thing where you don't want to lose a point because you forgot to put the units on there. Lose your points on the hard stuff, not the easy stuff. And so this is rate in, rate out problems. Okay, all it'll do is there will be some variation in the types of things it asks, but this is a general idea of the type of things it asks. You'll be finding the amount that went in, the amount that went out, total amount, and then usually another problem involving the two rates and adding the two rates together or subtracting the two rates. And so that's what these problems are about. There's only 10 of them in the assignment. You should be able to do those without too much trouble in the days that we're working on this. Um, but make sure that you're doing the problems, make sure that you're asking questions, and as always, happy mathing.